Define a sequence a sub 1, a sub 2, a sub 3, and so on as follows. A sub 1 equals 1, a sub 2 equals 3, and a sub k equals a sub k minus 1 plus a sub k minus 2 for every integer k greater than or equal to 3. This sequence is known as the Lucas sequence. Use strong mathematical induction to prove that a sub n is less than or equal to 7/4 all raised to the nth power for every integer n greater than or equal to 1. Now, if you notice, this recurrence relation here is the recurrence relation in the Fibonacci sequence. The Lucas sequence is very similar to the Fibonacci sequence. The only difference is that a sub 2 is 3, whereas in the Fibonacci sequence, a sub 2 is actually 1. Now, because we are going to be using this recurrence relation to prove the inductive step, then we are going to need strong mathematical induction. And in this case, because the gap between the largest index and the smallest index is 2 in the recurrence relation, and that means we're going to need to prove 2 base cases, and we're going to need strong mathematical induction. We won't need the entire inductive hypothesis, but we'll need certain parts of the inductive hypothesis to be able to prove P of k plus 1 when we get there. Let's start by identifying P of n, which is the predicate. The thing that we're trying to prove is this relationship right here. This is a predicate. And remember, we don't want to include the universal quantifier in the predicate. The predicate is just a sub n is less than or equal to 7/4 all raised to the n. Since the gap between the largest index and the smallest index is 2, then that means we're going to need to prove that this is true for n equals 1 and n equals 2. That's the first 2 cases starting from the lowest value of n that makes P of n true. We'll start with P of 1. What is P of 1? P of 1 is the statement that a sub 1 is less than or equal to 7/4 all raised to the 1th power. Now, I'm going to put a question mark here because I don't want to assert the thing that we want to show. We want to show that this is true. It might seem obvious, but we need to point out why it's true. On one hand, they give us what a sub 1 is. A sub 1 is equal to 1. That's the left-hand side. The right-hand side of this inequality is 7/4 to the 1th power. If you raise any number to the 1th power, you just get the same number, which is 7/4. And sure enough, 1 is less than or equal to 7/4. And this means that a sub 1 is less than or equal to 7/4 to the 1th power. And that's what we wanted to show. Now let's move on to P of 2, which is the statement that a sub 2 is less than or equal to 7/4 squared. To avoid confusing the reader, I'm going to put a question mark here so that I avoid asserting the truth of something that I want to show. Now, on one hand, a sub 2 is given to us as well. That's the left-hand side of this inequality. A sub 2 equals 3. On the right-hand side, we have 7/4 squared, which we can compute is 49/16, which written as a mixed fraction is 3 and 1/16. Written this way, we can see very clearly that 3 and 1/16 is larger than 3. And so that means that a sub 2 is less than or equal to 7/4 squared. Now let's move on to the inductive step. I always start the inductive step the same. The very first part of every inductive step is the same, and it's also the most important. Let k be an arbitrary fixed integer such that now k has to be greater than or equal to the largest base case, which in this case is 2. So k has to be greater than or equal to 2 in strong mathematical induction. In normal mathematical induction, there would be only one base case, and k would be greater than or equal to that number. But in strong mathematical induction, we want k to be greater than or equal to the largest base case that we showed. And we want to assume that P of I is true for all I less than or equal to k. This is the part of strong mathematical induction that's the most difficult to wrap your mind around. We're assuming that P of 1 is true, and we're assuming that P of 2 is true, and we might be assuming that P of 3 is true, or P of 4, or P of 5, depending on what k is. We're going all the way up to P of k. In normal mathematical induction, we just get P of k. And P of k is not going to be enough to prove that P of k plus... In normal mathematical induction, P of k is the only thing that we need to prove that P of k plus 1 is true. But in this case, P of k is not going to be enough to prove that P of k plus 1 is true. We are actually going to need to know that P of k is true and P of k minus 1 is true, and so that we can use the recurrence relation and prove that P of k plus 1 is true. And for that reason, we're using strong mathematical induction. So let's figure out what this means. This means that a sub k is less than or equal to 7/4 all raised to the kth power, and a sub k minus 1 is less than or equal to 7/4 raised to the k minus 1th power. And we can keep going. We're assuming all of these to be true for all I in between 1 and k, inclusive of 1 and inclusive of k. Now, we have justification to believe that these two are true, that a sub 1 is less than or equal to 7/4 raised to the 1, and a sub 2 is less than or equal to 7/4 raised to 2, because we just proved those to be true. In the inductive step, though, we're assuming all of these to be true, and we can use all of these tools to prove that P of k plus 1 is true. For this proof, we're only going to need these two inequalities to prove that P of k plus 1 is true. Now let's talk about what we want to show in the inductive step. We want to show that P of k plus 1 is true. What is P of k plus 1? This says that a sub k plus 1 is less than or equal to 7/4 raised to the k plus 1th power. Now I'm going to put a question mark here to avoid asserting the conclusion that we want to show. We want this line to be at the end of the inductive step, not the beginning of the inductive step. So I put a question mark there to avoid asserting the truth of anything. So how are we going to prove this? First, we're going to start with the left-hand side, which is a sub k plus 1. Now, since k is greater than or equal to 2, that means k plus 1 is greater than or equal to 3. If you notice here, the recurrence relation holds for every integer k greater than or equal to 3. Now, we don't need this recurrence relation for k. We need this recurrence relation for k plus 1. So I'm going to apply this recurrence relation to k plus 1 since k plus 1 is greater than or equal to 3. So let me clarify that k plus 1 is greater than or equal to 3. And since in the inductive hypothesis here, k is greater than or equal to 2, which is the last base case, that's perfectly convenient for us because then we can say that a sub k plus 1 is the sum of the previous two terms. That's the Fibonacci sequence part. So a sub k plus 1 is the sum of the previous two terms, which in this case, since we're starting at a sub k plus 1, the previous two terms would be a sub k and a sub k minus 1. And we know this to be true by the recursive definition of the sequence. Now we have a sub k plus a sub k minus 1. We know some things about a sub k and a sub k minus 1. They're both less than or equal to something. And so what I'm going to do is I'm going to take these numbers and I'm going to make them bigger. And so instead of putting equals here, I'm going to put a less than or equal to symbol. And this is where this proof is a little bit different than the previous mathematical induction problems we've solved so far. I'm going to replace a sub k with something that I know is bigger than a sub k. According to the inductive hypothesis, a sub k is less than or equal to 7/4 to the kth power. And also by the inductive hypothesis, a sub k minus 1 is less than or equal to 7/4 raised to the k minus 1th power. So to justify this inequality here, we can simply say that a sub k is smaller than this number here, 7/4 to the kth power, by the inductive hypothesis. And similarly, a sub k minus 1 is smaller than this number, 7/4 to the k minus 1, by the inductive hypothesis. These are two different parts of the inductive hypothesis that we're using to justify this inequality symbol here. Now, for those of you who are struggling with understanding why this inequality might be true, basically this is like taking the number 2 plus 4 and saying, well, this is less than or equal to 3 plus 7 because both of these numbers are bigger. And if you replace both of those numbers with bigger numbers, then you're going to get a bigger sum. And that's kind of what we're doing here, where this is the 2, this is the 4, this is the 3, this is the 7, and so forth. Now, this isn't quite what we wanted. We wanted to show that in P of k plus 1, that a sub k plus 1 is less than or equal to 7/4 all raised to the k plus 1. So far, we've shown that a sub k plus 1 is less than or equal to this thing, which isn't quite the same thing that we wanted. And so because of that, we need to do some stuff to this so that we get 7/4 to the k plus 1. Now, we're allowed to either simplify this, or what we can do is we can do the same trick that we did last time where we replace these things with bigger things to get bigger sums, and eventually, hopefully, we can get 7/4 to the k plus 1. Now, what I'm going to do first is I'm going to factor out a 7/4 to the k minus 1. So this is equal to 7/4 to the k minus 1 times 7/4 plus 1. Now, 7/4 plus 1 is the same thing as 4/4. So 7/4 plus 4/4 is 11/4. So this is 11/4 times 7/4 to the k minus 1. Now, this is the part of the inductive step where it's going to look like I'm pulling a rabbit out of a hat. This is going to be a really weird trick, but basically, I'm going to try to show that this expression here, 11/4 times 7/4 to the k minus 1, is somehow less than or equal to 7/4 all to the k plus 1. The way I'm going to do this is going to be strange, but when you see it, hopefully you can apply this technique into future inductive steps that are similar to this, which typically include induction problems with inequalities. What I'm going to do is I'm going to take this 11/4 and I'm going to write it in terms of 16ths. That's going to seem weird, but you'll see why in a second. This is the same thing as 44/16 times 7/4 to the k minus 1. Now, why would I do that? Ideally, what I would like to do is I would like to turn this 7/4 to the k minus 1 into 7/4 to the k plus 1. In order to do that, I need to absorb two factors of 7/4. I need to absorb a 7/4 into this expression, and then I need to absorb another 7/4 into this expression. Let me show you how I'm going to do that with this 44/16. That might seem like it's coming out of nowhere, and hopefully you'll see why this unsimplification of this fraction is going to actually help us solve this problem. Now, if I want to absorb two factors of 7/4, that's 7/4 times 7/4, which is 49/16. Now, this isn't quite 49/16. It's almost 49/16, but it's not quite. But what I can do to turn it into a 49/16 is I can replace this number with a larger number, 49/16. Now, this might look like I'm just cheating. I'm just replacing it with a bigger number. But the thing is, with inequalities, you're justified in doing that so long as you have the correct relation here, which in this case is the inequality symbol, less than or equal to. So I'm replacing this number with a bigger number. And if I replace that number with a bigger number, I'm going to get a bigger product here. 49/16 times 7/4 to the k minus 1, which then I can rewrite as 7/4 squared times 7/4 to the k minus 1. And now that they have the same base, I can simply add the two exponents together using the law of exponents. This is equal to 7/4 all raised to the k plus 1th power. And now let's talk about what we've done so far. What we've done is we started with a sub k plus 1. We rewrote it using the recurrence relation. Then we applied the inductive hypothesis. Then we tried to simplify it a little bit. And then we tried to replace these things with bigger numbers so that we can get to the biggest number here, which is 7/4 to the k plus 1. So what we've shown is that a sub k plus 1 equals this thing, which is less than or equal to this thing, which equals this thing, which equals this thing, which equals this thing, which is less than or equal to this thing, which equals this thing, which equals 7/4 to the k plus 1. We can summarize this entire inductive step so far by saying that a sub k plus 1 is less than or equal to the biggest thing here, which is 7/4 raised to the k plus 1. And that's what we wanted to show. This means that p of k plus 1 is true. So therefore, by mathematical induction, p of n is true for all n greater than or equal to 1. Thanks, everyone, and I'll see you in the next video.